you.
So we now arrive at the last talk of the conference, where it's a pleasure to introduce Anne-Marie Aubert, who will speak on C-star blocks and cross products for classical p-adic groups from Jussieu, Sorbonne Université, CNRS.
So thank you very much, Louis. So first of all, I would like to thank Hector, so Adrian, Hector, and Luis for having organized this wonderful conference, and all the previous speakers for their very interesting and very pleasant talk. And so I am very happy to be here, and I thank you for inviting me to this conference and give me the opportunity to give a talk. So I felt almost like if I am really physically in Valparaiso. So I remember my last time last year in January. So it has been my last travel before pandemic. And so here is a math building, so we can have a nice view over the Pacific Ocean. So now we can enter and go upstairs. And okay, and now we arrive to the seminar room. Okay, so I will talk about the joint work with Alexandre Afgoustidis. And so the one feature of the work is that it is working at the same time for any local field of characteristic zero. I mean, non-Archimedean field, p-adic fields, finite extension of QP, and also real field. With some difference, but the proof can work together. And the real case is much easier. And at the same time, it was the origin of our work. So in this talk, we will look at a special case of irreducible representation of a group G. So G will be the group of F points of a connected reductive algebraic group defined over F. And the representation we are interested in are the tempered irreducible representation. So we will denote by here T of G the set of equivalence classes of these representations. And this set is usually called the tempered dual of G. And it is an important space for several reasons. And one of the main reasons is that it is the support of a Plancherel measure. This set contains many interesting irreducible representations. They are all unitary, and it contains those whose Alexandre character extend to tempered distribution on the corresponding Schwarz space. So what we are what we have maybe more used to do here is when you look at the smooth dual or admissible dual of G, there is the Bernstein center, so the Bernstein decomposition of a category of smooth representation of p-adic group G with respect to pairs formed by a Levy subgroup and a supercuspidal representation of a Levy up to some equivalence relation. So here the role of a supercuspidal will be played by the discrete series, and it starts similarly by the work of Alexandre. So we start with M. Levy, subgroup of a parabolic subgroup P of G. So I will denote by N the unipotent radical of P, and by E2 of M, the set of equivalence classes of square irreducible representations of M. So the 2 is for square integrable. And we have the famous result of Arishama, which say that if you consider an irreducible representation pi of G, it always occurs in some parabolically induced representation from a representation of M, which is a discrete series, so square integrable representation. And moreover, the pair M and sigma is unique up to G conjugacy. And we can call it the discrete support of pi. So this plays the analogous role as the cuspidal, supercuspidal support for the smooth dual. And as we know in the situation of a smooth dual, this decomposition is in fact to film, and you would like to make it so you can think of each induced. So I like to think of such an induced representation of all the representation which occurs as irreducible component of such a parabolically induced representation as a representation which have a given color. And the point is that, and the idea is that you would like that the representation which share the same color as a nice structure. So if you just stick with this, this is too small. So we have too many colors. So we would like to put together representation which has color, kind of similar color. So and this is what we do. So this is just the analog, again, the analogous situation of what we do for supercuspidal. So for the Bunsen center, we allow to twist any supercuspidal representation by an anamified character of a Levy. So here we will do the same, except that the character, in addition to be anamified, will be assumed to be unitary, because we will stay in the tempered world. And so you will denote by XU of M the abelian group of unitarily anamified character of M. And the definition we take for a character to be anamified is that it is trivial on every compact subgroup of M. And this definition makes sense for when F is both when F is p-adic and also when F is real, is the field of real number. There is nevertheless a difference. So in the case of p-adic groups, this abelian group X U of M is compact, which is not the case for real group. And again, as for Bunsen center, we will look at the orbit by anamified unitary character of square integrable representation. So this will come all along the talk. So I will sigma, if sigma is a square integrable irreducible representation of a Levy M, we will denote by O its orbit under the group of unitarily anamified character. And we will call such a pair, a pair MO, a discrete pair. So we are interested in the following object, so that will be denoted by theta. So theta will be the G conjugacy class of a discrete pair MO. And so we will write it as follows. So when I use parentheses, it's to mean conjugation. And when I put square parentheses, is conjugation up to twisting by a unitarily anamified character. So it's the same notation that we are used to in the Bunsen center. And again, we can look at the we can partition the tempered dual using these pairs. And so we'll do it as follows. So if you start by P, a parabolic subgroup of G with Levy M, then you will denote by here Tg of theta, so the block defined by theta, which is the set of irreducible representation of G that occurs in a parabolically induced representation from a twist of sigma, where sigma is a representation of M which belongs to the orbit O. And this, we will say that we are considering, the block defined by theta is the set of irreducible tempered representation which have inertial discrete support theta. And so, and this gives a decomposition of the tempered dual attached to this component. So actually I didn't, so it's well known, but I didn't exactly know to whom we should attribute it. I mean, it's mainly in Alexandre, probably, but and for sure it is a consequence of the following result that I will give now by Roger Plymen in the 90s. And so the result of Plymen is considering a version of a group algebra of G, which is well adapted to the study of a tempered dual, and which is the reduced C-star algebra of G. So this algebra will play the role of a group algebra in the analogous role of a group algebra in the smooth dual. So to briefly recall its definition. So we fix a left invariant R measure on the group, and we consider the Hilbert space L2 of G. And then we have a left regular representation lambda on L1 of G. We can consider the C-star algebra, which is generated by the image of lambda. And this is the C-star algebra, which is called the reduced C-star algebra of G. And the interest of this, one of the interests of this algebra, a C-star algebra, is that its spectrum, so may be identified with a tempered dual of G. So it's a way to pass from the study of a tempered dual of R group G to the study of a dual of a spectrum of this C-star algebra. So it's pretty much analogous to what we have for smooth representations. And then for real groups, in 1985, Alain Valette gave a decomposition of this algebra as a direct sum of sub-C-star algebras, such that each of them is attached to an inertial component theta. And 5 years later, Plymen extended the result to the case where F is p-adic. So the result is the same, and in particular, this provides a proof of what I have given before about the decomposition of the tempered dual in blocks, inertial blocks. But the proof, so the result is same, but the proof for real groups and for p-adic groups are very different.
Can I have a quick question? Is it possible to give a definition of the typical component in the C-star algebra decomposition? What is C-star G semicolon theta? How is it defined?
Okay, so I think I would maybe I give a okay. It's
If it is complicated, then don't worry about it.
I mean, it's not difficult, but it's complicated to explain. So
okay,
maybe,
all right, thank you.
And sorry, and and actually the point is that we will. So I will not give a definition, but the object of a talk is to find a more simple way to view it. And so we will. So our objective is to replace this subalgebra by another algebra, which is much more easier to understand. At least I think so. And this second algebra will be the result that is that this second algebra, under some certain assumption, will be Morita equivalent to this one. So in for real groups, Wassermann in 1987 actually described in a confounding note this algebra, and the proof was announced in the note, but after that it did not appear. And so we'll see that it is a consequence of our result. So, but to explain this, I need to introduce more material. And so this is what we do now. So first, I mean, it's really follow the same idea as we are more familiar in the case of Bernstein. In the case where the representation of M are not discrete series but supercuspidal representations. So we'll consider the stabilizer of the representation sigma. So we start with a square integrable representation sigma of M, and you consider the element in the normalizer of the Levy, which fixed the representation divided by the Levy. And it's so this group W sigma is almost finite. It's finite first, and it's almost a Y group. It's as proved by Knapp-Stein many years ago. It admits a decomposition, W prime semi-direct product with R of sigma, where W prime sigma is the Y group of a root system. So this one is a finite Y group. And this root system can be defined via the Planck-Reil measure. So just recall the definition. So let's denote by delta the set of roots for GM. And to each element in delta is attached a Levy subgroup M alpha, and we have the Planck-Reil measure for that group M, that Levy mu alpha, which contain M, and we can consider the delta prime, the roots, the subset of roots, such that the mu M alpha of sigma is 0. And so this is, it can be checked that it is a root system, and the group W prime sigma is, by definition, the Y group of this root system. And then when we can fix a positive system in delta prime, and as usual, we have a component of that group W prime sigma in W sigma by considering the set of the element in W sigma which preserve a positive roots. And so this define R sigma. Also, if you denote by H the space of the induced representation from parabolically induced representation of sigma, and if you take R a non-trivial element in this R, what we call it an R group R sigma, then the Knapp-Stein-Silberger give us non-scalar self-intertwining operators of H, and the map which send R to this operator defines a projective representation of R sigma on the space H. And for real group, actually this projective representation can be always linearized, but not for p-adic, and so it's can find a true representation. But for p-adic groups, this is not always the case, and so it's occurs that there exists two cocycle which does not of the group R sigma, which does not always split. And Arthur dealt with this problem by considering a certain central extension R sigma tilde of R sigma over which the cocycle splits, and it would be more convenient to work with this extension instead of the group R sigma. So just a few things about this this object. So we have this central extension. So it means that we have a short sequence, and where Z is central, and the two cocycles on this extension. So we get actually we have a cocycle eta sigma, and it's also possible to choose a map xi sigma with value from the extension with value in C, that splits the cocycle in such a way that we have the following formula. So you can express eta sigma by this identity in terms of xi sigma. And Arthur shows that the irreducible component of the induced representation, parabolically induced representation from sigma, are in natural bijection with a set of irreducible representation of the extension of R, which admits a given Z sigma central character, zeta sigma, which is actually given by considering the inverse of this xi sigma. So these are very useful Arthur result, and then with this you can consider another group which is very similar to the W sigma, in which we have replaced the R group by that extension R sigma tilde, and we can extend the map above eta xi and eta to this group in such a way that you keep this formula, the relation between eta and xi still works. Moreover, this extension arises with a central idempotent acting on the group algebra of R sigma tilde, and which has the property that if you consider the image of a group algebra of R tilde sigma, you get the twisted algebra of R sigma twisted by the cocycle eta sigma. So these are the objects we need to formulate our result. And by comparison to Bernstein Center, we will consider not only the stabilizer of a fixed representation sigma, but its inertial stabilizer, in the sense that it is the stabilizer not of sigma but of the orbit. So it's the normalizer of theta, of m and theta, mod m. And okay, and until now we have made no assumption, but now you will have two assumptions. So the first one is that the action, so the group, this inertial stabilizer W theta acts on the orbit O, and the assumption is that this action has a fixed point. Okay, and which means it's just a way to reformulate it, which means that if you have the fixed point, if you call sigma such a fixed point, then the stabilizer of sigma coincide with the one of theta. So the first result, I mean, the first things is that when f is real, the group W theta always admits a fixed point. And this is very easy to see. You can look at the Levy and you can decompose it by using its Langlands decomposition as M0A, where M0 is the group generated, the subgroup generated by the compact subgroup, and A is the split component of the Levy. And now if you take an element tau in the orbit, then you restrict to A, and you get a certain unitary unramified character chi of M, and you twist sigma by the inverse of that character. We twist the tau by this the inverse of that unramified character, and then this twist that we call sigma is trivial on A as well as all is conjugate. And it provides a fixed point for the action of W theta on O. Okay, so it's very nice. So there is no, which means that there is no, the assumption 1 is always satisfied in the real situation. And what is the situation for p-adic groups? So in general, we do not know. We do not have a counterexample. But we do not have a proof that this assumption is always satisfied. But you manage to prove it in the case where G is a symplectic group or a quasi-split special orthogonal or quasi-split unitary group. So we hope that it is always the case. But this is not enough. Having a fixed point will not be enough to get the result we want, and we will need a second condition. We need that we have a fixed point, but we also need that this fixed point has good property. So it's what we are now introduce the notion of good fixed point. So fixed point, it would be said good if the two following properties are satisfied. So we have the decomposition. So we start with sigma. So sigma will be, in some sense, a base point in the orbit. And you'll say that sigma is good if for every point tau in O, so we have a corresponding Knapp-Stein decomposition, the finite Lie group W prime tau is contained in the corresponding group for sigma. This is the first condition. And the second condition is that the R group attached to tau is isomorphic with a subgroup of R sigma. And the nice things is that when F is real, this is always possible. We can always find a good fixed point. And actually, if you look in the paper by Knapp and Stein from the 80s, the first property is proved there, but the one regarding the finite Lie groups, and the similar argument allow to prove that the second property is also satisfied. So now, what is the situation when F is p-adic? The answer is that it's not always true. I mean, we have situations in which we do not have a good fixed point. And I will explain a bit more on this later. But first, assume that we are in the good situation. Assume that we have a fixed point, which is good. Then we can prove that we have a strong monetary equivalence. So unfortunately, I didn't give a definition of this this C-star component, but the point is that it is what we prove is that it is Morita equivalent to the following cross product algebra. So you consider the image by this the idempotent p tilde of the following algebra. So we on one side we first consider the group the continuous function on the quotient of O by the finite value group W prime sigma, and you take the cross product by the Arthur extension of the R group, and then you take the image by the idempotent P. Or if you prefer, you can take first, which is also same thing as considering CO mod W prime sigma cross product with by P tilde of R tilde sigma. So pi tilde is acting non-trivially only on R tilde sigma. So the first remark is the following. So when F is real, there is, as I have already said, there is no need of extension. So R tilde is just R sigma and P tilde is the identity. And so we recover the result of Wassermann, so Wassermann theorem, and the proof and give a proof. And so it is, as far as I know, the first available complete proof of Wassermann result. And when F is a p-adic field, special cases were proved by Plymen many years ago in the 19th with students of him. And the point is that the cases proved by Plymen are always cases in. So we have the Knapp-Stein decomposition of W sigma as a semi-dialog product of these two groups, and they managed to prove it in the case where one of the group is equal to W sigma. So for instance, W prime is equal to W sigma, and then R sigma is just trivial, or the other extreme case when there is no the group W prime sigma is trivial and R sigma is all the group W sigma. And our proof, so the argument we use in the proof are mainly inspired by the proof of Plymen's results, and also our proof is uniform, so we do not need to. I mean, it's for any local field of characteristic 0. So in the remaining time, I would like to show you more precisely what are good fixed points and when you can find them. And the point is that for quasi-split classical groups, we obtain we obtain a characterization of good fixed point. So they are not occurring always, but it's possible to characterize when. And first, start with the bad things. So give an example of a bad fixed point. So by bad, I mean that. So by bad fixed point, I mean that there is no, that the point is not good, and also there is no good fixed point. In fact, if we change the point to another fixed point, we cannot find any good fixed point. So this is a very natural example. So look at SP4, and when the levy is a torus, so L should be M. And then you just take for sigma the trivial representations. of a torus, and then the group, the group, of course, if it is the trivial representation, it is clearly fixed. It is a fixed point. So W theta coincide with W sigma, and so it is the Y, and which coincide with the Y group of SP4 with respect to that torus L. And so we have a fixed point. And now if you take any unitarily unmodified character chi, you can consider the group, the R group of sigma. So sigma is here just the identity. So of sigma tensor by chi, and it is a subgroup of the group generated by these two element scene changes element C1 and C2. And we can check that this element belongs to, so Ci belongs to R sigma tensor chi, if and only if we have chi square is equal to 1 and chi square is equal to 1 and chi I is not trivial. And from this, it's easy to see that our assumption to be, and the condition to be a good fixed point is not satisfied. So what is the hope to get a fixed point? Actually, there still exists many cases where we have good fixed point, and so let's try to give you to show you how we can characterize them. So start with, I will just look at the symplectic groups. So the other groups, I mean, unitary and special orthogonal are rather similar. So start with M Levy. So it will be a product. It will be isomorphic to a product of copies of small GLN and one group M prime, which is also a symplectic group, but I will call it SP2QF. And so this is just to give you the description of by matrices of the shape of a Levy. So we have a G1, GR element on the, it's a block diagonal matrices, and so we have a GR element in the GR block. Each block GI is in some group GL and I, and some element in the middle which belong to the small group SP2Q of F, and the other element are obtained by considering the transpose with respect to the off diagonal and then the inverse. So this is just the usual shape of a Levy, and you can of course compute the Y group attached. So WGM is by definition the normalizer in G of M mod M, and as we have seen in the case of SP4, it is generated by two kinds of elements: permutation of block of the same size and scene changes, that I denoted by CI. And if you consider the element in A, so the block permutation, we get a certain subgroup, which is isomorphic to a symmetric group, CS sigma R. And the group, so and the scene change given normal subgroup of a group, and you obtain that the group is, that it is well done, a semi-direct product of that symmetric group by this group normal subgroup C. Okay, so now I will start with a given discrete series, so this square interval representation sigma of M, so, and we consider is the block decomposition following the block decomposition of M. And we denote by a sigma check for the following representation. And also in the case when we have block of a GLN block with the same size, I will say that sigma is a twist of sigma to mean that sigma j is equivalent with with sigma tensor by a unitary unmodified character. So this allows to give to obtain a description of a group W theta. So here is the description. So the group W theta is generated by transposition. That for when Ni is when for same block and when the representation sigma is a twist of sigma j, by the sin chain Ci, for which the check sigma I is a twist of sigma I, and then and by products of Zacher transposition and Ci Cj. In the case where sigma check sigma I is a twist of sigma j, but not of sigma I and not of check sigma j either. So we have an explicit description of all the group we want. And so we all have two things that you know some of you know very well. So consider the condition when consider the special case where the levy is maximal. So it's a product of two blocks in the group GI, which is given by two other block. And we will say that the representation rho of GL2 of Ni satisfy a certain condition Ci2 if when you induce the representation from Mi of a tensor product sigma tensor 2 when this representation is reducible. So this has been studied by in particular by Goldberg and by by Shady. So in particular, if rho satisfies that condition, it must be self-control gradient, and I mean the sense that checked rho has to be equal to rho, and also some remark about this condition Ci2. It's a condition of arithmetical nature, and in particular in the case where rho is superhospital, Goldberg and Shady gave a precise criterion using the residue of standard intertwining operators for which the condition is satisfied. Okay, so we will need the torsion group of the representation of GLN, so just the element T of sigma I, which is a finite group of unramified character, unitarily unramified character, such that if you consider the check of sigma I tensor by chi, it is equivalent to sigma I tensor by chi, and we can reformulate it to say that to have a more easiest description, which is the set of unitarily ramified character chi, such that chi sigma I tensor the square of chi is equivalent to sigma I. And we can also introduce an equivalence relation to the set of number 1 to R by saying that I is equivalent to J if a block of same size, and if sigma J is either a twist of sigma I or a twist of its dual. And then we can make the following definition. So we start with a representation sigma, discrete series, and you assume that it is a fixed point for the action of W theta, and we consider and we fixed omega and subset of 1R, which is an orbit for the relation equivalence relation we have just defined, and we will say that omega is weakly R relevant if for any element in the orbit that is among the representation sigma I tensor chi, with chi is in the torsion group of sigma I, there is at least one representation which satisfies the reducibility condition Ci2. So this is weakly R sigma relevant, and we have something which is more relevant, much more relevant, that we call super relevant. If for I, so omega will be, the orbit will be we call super relevant if for I in omega, the representation sigma I tensor chi, where chi is in the torsion group, all these representations satisfy the condition Ci2. And then we obtain the following characterization of the existence of a characterization of good fixed point. So start with sigma, a fixed point. So we have already seen that it's always possible to find one. And then this fixed point is good if and only if an orbit can be weakly relevant only if it is a singleton and is, in addition, it is super relevant. So the condition looks quite strong, but anyway, it exists, and it's possible to, if you look at an example, you will see that we can find good fixed point in situation when we might have W theta, which is a real decomposition of two groups, W prime and R sigma, in which both of them are non-trivial. Okay, and okay, so for the situation is rather similar for quasi-split unitary group and for split odd special orthogonal group, and it works also with slightly more work for the quasi-split form of even special orthogonal groups. So here is the reference on archive for paper, which is currently submitted. So and of course is not the end of the story, because it's only a part of it. So what could be the sequence? So first first we can look at the same situation of good point fix in other group. For instance, for SLN, because in the case of SLN, the R group and everything has been also computed by Goldberg, and also for other kind of classical groups like G spin or GSP, and the kind of group, because they are resolved by Ban, Goldberg, and Choi for several of this group, which computed also the R group. But perhaps the first things would be to understand better what is the situation in the case of bad fixed point groups, because at the moment it is not, we do not have a proof of a statement, but even than that, we do not have more than that. We do not have a statement, so it is not clear, because what should be something that I should have said is that if we do not have a good fixed point, we can show that it's not. We show in the paper that it is not possible to have the theorem cannot hold. So cannot hold true. So something more subtle should happen, but it's not clear what it is at the moment. Another direction will be to study what I call the mirror picture. So using long-length correspondence, assuming that we have it, when you get a similar picture on the Galois side, in which the long-length correspondence should parameterize the irreducible temporal representation by bounded enhanced long-length parameter and discrete series by discrete enhanced long-length parameter. So it's possible, I mean, if you assume long-length correspondence, it's of course possible to state the same result. I mean, what should be the result in the level of enhanced long-length parameter, but maybe it's also possible to prove it directly for enhanced long-length parameter. And another direction, which I have not, another thing is that, of course, we have Bernstein center. So what is the link? And Bernstein center works also for temporal representation. So what is the link with the block decomposition here and the block decomposition in for the Bernstein Center, but I do not have more time. So thank you very much for your attention.
Are there questions for the speaker? So I was curious about the condition CI. Does it go to the structure of the L packet, or is it more of an R groups property?
I think it's close to L packet. Yeah.
Mm-hmm.
Because it's really a condition on reducibility, which can be, I mean, it's a condition about the intertwining operator. So it's really about L functions. Yeah.
Okay, so then, and if the author, one can choose the L function. Okay. Are there other questions? Or if not, let's thank the speaker again. There will be a discussion session with Anne-Marie, but because it is the last talk, well, I wanted to thank all of the speakers for giving such wonderful talks in Valparaiso, and also all the participants, because without you, this would not be such a lively conference. Then, of course, I'm very happy that to work with Adrian Centeno on the organization of this. And we even recruited a last-minute backup organizer with Hector del Castillo. And so many thanks to everybody. Jessica Finson at some point helped us set up the Gather Town, which was nice for the virtual coffee breaks. So again, thank everybody. Thank you all.